And as you can see from my title, I kind of strayed a bit far from the original goals we had back then, when it was more about math of data science and comprehension still. But in my defense, I maybe have a good reason, because a bit has happened since the trimester program in 2016. And one of the new results, at least in a field where I also developed, are things like this. So since 2019, we have the actual first functioning quantum computers with a reasonable number of qubits. The best example is the Google Sycamore chip. I will talk more about that later, which has 53 qubits. And so this is big enough to actually do some non-trivial things. And here, actually, I'm very proud. I have some next generation silicon chips for ion trap quantum computers that are constructed in Innsbruck. So maybe I can pass them around if you actually want to see.
What is it?
This is a prototype of a quantum chip where they try to like load into individual ions in order to do actual computations in the future. And this is the first step in kind of going into a standardization of this type of technique. Okay, so
I understood what that is.
this is a quantum chip. Kind of, it's more a case, but if you look at it closely, you can see a very, very thin line in the middle. And this is where the experimentalists actually in the lab put individual atoms. They kind of hold them in place with electric fields, and they use ground state and first excited states to do quantum computations. And my talk is going to be about that, because in a nutshell, like really technologically, quite a lot has happened in the last 5 years, and we are having these early generation quantum computers that are becoming too large to actually simulate them on a classical computer. So like 7 years ago, we could just use a laptop and pretend it to be a quantum computer with 5 or 6 qubits, because that you can still simulate, but today's devices are becoming too large. But at the same time, they are not perfect. They make a lot of errors actually, and errors accumulate over the duration of the computation. And so there's a hard upper limit on the complexity of the actual computations you can do, simply because you run out of runtime. And so it's actually a very non-trivial question to take these quantum devices and do something useful with them. So somehow they're too big to simulate them on a classical computer, but that doesn't mean that they can do anything useful or interesting yet. And the quest for quantum advantages is to try to find problems. They are admittedly very, very stylized, where you can justifiably show that this quantum device can do something that even the world's largest supercomputer couldn't reproduce in a reasonable amount of time. Again, this doesn't yet mean that the problems themselves are actually interesting. It's more like an unfair race skewed towards the quantum computer so that it can outperform supercomputers, hopefully. And in my talk, I want to talk a bit about these things and maybe some new contributions that we, I think, could contribute. And they're actually based on facts and techniques that I learned here at the trimester program, techniques that we use and maybe also have heard throughout the course of this workshop. There will be 3 occasions in my talk where I will mention some techniques that are maybe very familiar to you, but the jargon is a bit more on the physics side. And to get us off, because it's the last talk of the conference, I also want to give you a bit of a background, what quantum computing actually is, what it tries to aspire, and where we are now. And then in the second part of the talk, I want to introduce some new way of extracting information from quantum computers called classical shadows that are essentially based on matrix Monte Carlo sampling with random unitary transformations. And this turns out to be a very, very powerful tool that you can later use to synergize early time quantum computers with powerful classical hardware to get something that is better than the individual parts. And at the very end, as I promised on the head slide, I will always also try to motivate new types of quantum advantage that are different from the quantum supremacy circuits that you might heard about, that actually result from looking at scenarios where these matrix Monte Carlo techniques have to fail. So these are not only interesting because they work well for certain examples, but if you look at where they struggle, you can actually find a new window for new types of quantum advantages. And I know that kind of like the language and the terminology I'm using is maybe not very standard for audience, so please feel free to interrupt me at any point if you have questions, or like if I should clarify something. Okay, so in a nutshell, from a very high level perspective, what is quantum computing? Actually, what do these people like Google or the Innsbruck guys who built these things actually try to achieve? And in a way, it's an attempt of reinventing the wheel of computing. Kind of a normal computer like the ones we use today are actually based on physical principles. We use currents to carry binary information, 0 and 1. And then we use transistors based on classical electromagnetism to process this type of information in circuits that execute logical functions, right? And with a quantum computer, we are trying to do the same, but where the individual carriers of information are not current anymore, but they are so small that they adhere to the rules of quantum mechanics. So concrete examples, I think the most instructive one is the one on the left, would be an ion trap quantum computer. This is an ion trap quantum computer. And there you try to isolate individual atoms in the air by ionizing them so they become electrically charged. And then you can use electric fields to pin them in place. And atoms have a ground state and many excited states. And what you can use is you can say the ground state is my logical 0, and the first excited state is my logical 1. This is binary information. And I try not to use all the other excited states so that I only have still 2 levels of information. And then you could load in bit strings into these things, right? 0, 1, 0, 1. But the interesting thing is that they are so small that when I start to, for example, shine laser light on them or like do some physical operations, then they behave differently than classical current would. And that there are quantum mechanical effects that you can use in order to do single qubit transformations or maybe correlate nearby particles. And one way to do that is ion trap based quantum computers. You can also try to do the same with light. You can try to use individual photons to store binary information, typically in the polarization. And today the leading technology are actually so-called superconducting circuits, which you can view as very, very small wires, short circuit wires that are superconducting, where current can either flow in one direction or into the other. And you store the information based on the current flow, and then you can interact with that because current that flows produces a magnetic field. So these are the 3 leading technologies where they really try to build a new type of computing device bottom up by starting from the fundamental carriers of information and then using physical forces, typically laser light or something, to force these to behave in a certain way. Okay.
Are all the 3 equivalent in the sense that they all are modeled by the qubit?
Yes, exactly. All of them are artificially constructed so that the quantum mechanical systems always only have 2 degrees of freedom so that we can model them in the qubit picture. While most of them actually would have a continuous family, but then it would be more difficult to construct a binary or like, let's say, a finite computing device. So people actually work hard to isolate 2 degrees of freedom so that you can model them with a qubit. Yes?
So is there potential, you think that if you have 1 or 2 states,
yes,
there could be more information?
Yes, exactly. Because right now, these are not really scalable. Like they have 50 qubits or something. And like the original vision was to like take inspiration from classical computers and then just do a statement that you could also encode any digit in a sequence of bits, but that produces always an overhead, right? So if you're kind of like the number of qubits you have is small, then this makes sense. And this is actually an area that is now actively pursued because it seems to be difficult to scale these systems up. Very good point. Yes.
I just have a maybe nice question. So my understanding is that these quantum effects are always on a very small scale.
Yes.
So it makes sense that ions and photons.
Yes.
It seems like to me that these superconducting circuits are kind of much larger.
Well, they are nanostructures.
Okay, so they're also
Yes.
small.
Yes. But you're raising a valid point here. Because the problem is if you want to let this qubit, this superconducting circuit talk with this superconducting circuit, it gets more difficult over time. Kind of over distance, sorry. But very good point. But they are also really, really small. Okay, so why the hell would we want to do that? Computers already work pretty well. But there's actually some potential gain here because the laws of quantum mechanics as a theory and also in physics in experiments are different from the classical laws of electromagnetism that govern the functioning of a classical computing device. there's now additional possibilities, but also restrictions if you think in terms of computing. So there's genuine quantum effects that you might have heard about, like the superposition. Schrödinger's cat can be both dead or alive. I don't want to go into details. You can use the concept of entanglement, which is very strong correlations between two quantum particles in order to do things that you couldn't do in a classical computing device. But a bit closer to algorithm design, what is also true and actually very useful is that on these quantum machines, you can do extremely fast transformations. Like a fast Fourier transform on a quantum computer would be exponentially faster because the runtime would only be logarithmic in the system size. And this helps you in algorithm design. And then you can also try to be a bit more empirical and use optimization, solve optimization problems based on physical principles, like cooling down in order to solve an interesting combinatorial problem. But quantum mechanics doesn't have a reputation of being necessarily a very easy theory and very easy to handle. So there's also adverse effects that a classical computer doesn't have and that you have to take into account when you want to work with a quantum computer. Like a very basic but extremely annoying thing is the so-called no cloning theorem. If I have a qubit, I cannot copy it. If I look at it, I will destroy it. It is impossible to take a qubit and copy its content without destroying it. And so simple things that we use in everyday programming, like copy this string, is just not allowed. And also remember that even if we load the information into these very, very small particles in these qubits, and then we do some physical effects upon them so that they perform a computation, but in the end, this is not a bit string. This is still a quantum mechanical correlations between many qubits. And we somehow have to access that in order to get information, extract information about the result of the actual computation. And these measurements are destructive in the sense that if you look once, you will destroy the entire working memory of the quantum computer. And if you want to look again, you have to redo the entire thing from the beginning. And what to make matters worse or better, which will be the content of the next part, is that the result you get is a bit string, but it will be a random bit string. And the result of your computation is encoded in distribution. So you always have to repeat quantum computations many times, which introduces an additional inner loop that you have to take care of. And the most difficult, the most glazing problem is that these systems are extremely fragile. Shouldn't be surprising if you have individual atoms floating around in midair. So we really have to work hard to get the accuracy we need to actually manipulate them. But also it can happen that if your quantum computer is maybe here and then a tramway goes by and there will be like a small magnetic field that can really affect this entire thing. And the last conceptually important thing is that you can in principle classically simulate these things. There's a classical description of quantum systems. The only downside is that the complexity scales exponentially in the number of qubits. So if you have 50 qubits, if you are willing to invest 2 to the 53 kind of like floating point numbers, then you can do everything that the Google quantum computer can do. So the best you can hope for are exponential improvements. But don't expect quantum computers to solve outlandishly difficult problems or collapse the polynomial hierarchy. They can't solve uncomputable problems, for instance. The best you can hope for is an exponential speed up. And if you actually want to do something useful with them, which is arguably the main reason why we're actually building them, then you have to somehow balance these blessings against these curses. And I can tell you from experience that in every concrete instance, that's not necessarily easy. And history shows that. Today, we know about 65 problems where we have a provable and a quantum algorithm, a quantum procedure that provably outperforms the best known classical routine, but we've been looking for them for 30 years. Peter Shores came up with 2 of them in 1994, and 65 algorithms for a computer is really a small number.
What does this statement mean? Sorry.
What?
What does this statement mean? That it probably is better than
like you can try to build up quantum algorithms by kind of like writing a set of instructions in the form of a circuit. And the set of possible instructions you can do is strictly larger than what a classical circuit could do, because you could do these, go into superposition or something. And then the size of the circuit, the length of the instruction set that you have to do is a good proxy for runtime. And then it can happen that you can solve a certain important problem like prime factoring.
We don't know that prime factoring is actually.
Exactly. Yes, exactly. That's also another problem. Yes. Kind of like what I'm saying here, we know roughly 65 hypothetical quantum algorithms that are better than the theoretical guarantees for the best known classical algorithms. Thank you for helping me clarify this. But really, they can only solve certain problems much, much better than our current computers can. But for most problems, they're going to be useful. Trust me, you don't want to use an Excel table calculation program on a quantum computer. This is like kind of the worst possible application. And so you should really not view them as quantum computers. I think the term is misleading. You should much more think about them like of a graphical processing unit, of a highly specialized coprocessor that you outsource very specific problems to, that it can solve much, much quicker than a CPU could do it. So you should really view it as a coprocessor designed to augment the computing hardware we already have. Okay, and again, I already alluded to that. One of the big quests in the field for theoreticians and also for experimentalists is to actually kind of demonstrate that this entire endeavor is actually worthwhile, that it does something interesting, other than like being very, very difficult to build and very, very expensive. And this is called the quest for quantum advantage. And it can be roughly summarized as kind of like identify use cases, identify problems where such a quantum coprocessor can really make a difference. And for far term, like for very, very big and very accurate quantum computers, we have very good use cases already, like Shor's algorithm for factoring and discrete logarithm in polynomial time. But in this near-term regime, this regime where we are now, where the quantum computers are noisy, they are not big, and you cannot run computations for a very long time, we don't have that many use cases or applications. In fact, the only big result in this regard are these Google supremacy circuits, where Google in 2019 showed that their device is capable of doing something in milliseconds that a classical supercomputer would take at least days to do so. But this was a very unfair race because the challenge they posed is pretend to be a quantum computer doing a random computation. This is pretty far away from a useful use case. But in pretending to be a quantum computer, executing a random set of instructions, they could really show that their 53-qubit chip convincingly outperforms the best known classical supercomputer. And they also have complexity theoretic support for that. Okay, but apart from that, we don't know that much. There's a lot of heuristics, there's a lot of hype, there's a lot of interest, but we don't know many justifiable examples where quantum computers can make a difference. Are there questions at this point? Very good. And so I want to like maybe explain the first contributions that we made, very much inspired by ideas from randomized data processing, from Monte Carlo sampling. It's a technique that's called classical shadows. It's pretty widely used today, but it's really an efficient way of extracting information out of a quantum system. And as you will see in a minute, it's really just matrix Monte Carlo. And in order to motivate the problem, if you agree with me, and I hope you do, that the quantum computers will not replace the computers we have today, but will always serve as co-processors empowering these devices, then there will be problems at the interface. Because the quantum computer operates on the quantum mechanical scale, and the classical computer operates on a larger scale. And so there will be information transmission bottlenecks, two of them. Once, when we have to like input a problem instruction to the quantum computer, tell him what to do. And then once the quantum computer has completed its computation, we also have to extract the relevant outcome in order to feed it back into our classical computer, which is the readout problem. And both of them are very interesting. The input problem, you can broadly classify as quantum software, but also quantum hardware design. You maybe want something in the long term like assembler, like kind of something that tells you how you can send instructions to the quantum computer. What interests me more, because it's a bit less, let's say, more of the same, is the converse direction, the readout problem. And you can summarize this as a quantum to classical converter. The question is, once the quantum computer has completed its computation, how can we efficiently extract meaningful information we need in order to empower and go on? And this readout problem is really plagued by these quantum curses I mentioned before, most notably the collapse of the wave function. If I perform one measurement, I kind of destroy my entire working register. And in order to get the next look, I have to redo everything again. But also the fact that the measurement outcomes I get are actually random, and the underlying distribution can be complicated and very correlated. And let me just emphasize that the readout problem is an actual bottleneck that has negated quite a few quantum advantages of believed algorithms. Just because it isn't enough that the quantum computer does something super powerful, you also have to get access to the result, what it actually did. Okay, and so the readout problem is now, I want to change language a bit. The readout problem is really that these correlations, the results of a quantum computation, are encoded in correlations between these qubits, and we only have sampling access to them. So we can measure each qubit, and then we'll get a bit string, and the information is encoded in the correlations there, which can be very, very non-trivial. But every time we press the button, we run the computation, we only get one sample. We sample from an underlying distribution. And so naively, you would guess that you would need exponentially many repetitions maybe to learn the entire correlations behind it. And this is very expensive. And it's really kind of seemingly annoying. But if you have sampling access to a complicated object, think of a large matrix, then for us, this is not necessarily a bad thing, right? Because with sample access, you can try to do Monte Carlo approximations. Like in Monte Carlo approximations of big data matrices, the idea is typically that you start with something very complicated. In our states, is the correlations defining the result of a quantum computation. If you have n qubits, this is a 2n by 2n matrix. But we get sampling access to that. And so we could use that to maybe do an empirical approximation based on importance sampling of something that looks much, much similar, of maybe uncorrelated objects. Okay? Yes?
Sorry, I'm not sure I understand this part. So what is sampling access? What do you see? You see just ones and zeros?
Yes.
Like,
and there's like, I will explain it later. This is just a high level picture. Like having sampling access to something complicated is not only bad because it allows you to do important sampling. And if you maybe think a bit, this allows you to do like some efficient approximation in terms of objects that are simpler in the sense that they are not correlated anymore. Okay, and this is actually what we did. The Monte Carlo paradigm kind of like ensures tractable approximations of these complicated objects. And if you try to do these things in classical data science, then the most difficult part is typically sampling from the underlying distribution. But we found a way to outsource the actual sampling process to the quantum computer itself, because that's what it does. It gives you outcomes that, where the probability depends on the underlying quantum system. And on a high level, what we achieved is a combination of very simple quantum software, very simple instructions on a quantum computer that you do just before performing the measurement and getting the sample, and conventional software. And both of them are kind of very, very simple and tractable. Yes?
Is the state space like the samples instead of size to the n?
Yes.
Or 2 to the n?
No, the samples are of size 2 to the n. They're bit strings.
Of size to the n.
There's n bit strings of length n. There's 2 to the n of them. And the underlying distribution is encoded in all possible correlations. So this is a 2 to the n dimensional distribution underlying it. Okay, and so the Monte Carlo method we did to achieve this is actually not so complicated. And in order to start with that, let's think about a big matrix, or like doesn't even have to be big, a matrix A that is maybe like a covariance matrix, a matrix that is positive semi-definite, and let's say for normalization reason the trace is normalized. Then one of the simplest way to do Monte Carlo sampling for such an object is to take the diagonal, the matrix is positive semi-definite, so the diagonal entries are all non-negative, and the trace tell you they sum up to 1. And so I could do important sampling on the diagonal in order to try to approximate the matrix, right? This is at least a meaningful sampling process because all the probabilities are non-negative and sum up to 1. Yes?
What are you sampling? You're sampling rows of the matrix?
Not just individual diagonal entries. Kind of like,
Then you're only going to get the diagonal.
yes,
Right?
exactly. You only get the diagonal of the matrix. So this is a bad Monte Carlo approximation. It works if you only are interested in predicting diagonal properties. Okay, so this is maybe doesn't quite cut it, but this type of diagonal sampling actually is exactly what happens in a quantum computer. The quantum computer, the underlying correlations are a big covariance matrix, 2 to the n by 2 to the n. And if you perform a measurement, then it will sample random indices of the diagonal entries according to the associated weights. But if you just sample from one diagonal, you have no chance of getting the actual correlations, right? Because they're off diagonals. So one thing you can do is to do a random unitary transformation before looking at the diagonal. So instead of just sampling from a fixed diagonal in order to get a Monte Carlo approximation, you could first rotate the matrix in a random direction and then do sampling from the diagonal. That's maybe a smarter way of doing Monte Carlo approximations, because this way you can actually see off diagonal entries. Okay. I just do Monte Carlo sampling where in addition choose a random unitary transformation to rotate the diagonal around. And if the original matrix was positive semi-definite and trace 1, then the rotated matrix will also be positive semi-definite and trace 1. The diagonal will be a valid probability distribution, and I can sample from that. And now the question is this kind of like a good Monte Carlo approximation? And the answer is yes. And this equation here was actually something that was pretty popular back during the last trimester program, because if you actually look at what the expected value is, if I also average over all possible unitary rotations I do, I will get something that looks very similar to the expressions we looked at in 2015 and 2016 to solve the phase retrieval problem. Just have a look at it yourself. I just rewrote it. And in the second line, what you get is kind of an expectation where you have an inner product, a quadratic form defined by the matrix, evaluated in a random direction. And then you kind of look at the outer product of the random direction itself. And if you can think like a random direction is a bit like a random Gaussian vector. So you can do Gaussian integration. And what you will see is that kind of this type of Monte Carlo sampling, where you also have a random unitary direction, actually tells you something about the original matrix. The result of this type of averaging is the original matrix. It's shrinked plus an additional contribution that is the identity matrix. Like in the phase retrieval literature, we did that as kind of like as a first step for facelift, for instance, and this was called a near isotropy condition. But this type of Monte Carlo sampling, if I just do this, I will get an average that has at least some signal of the original matrix in there, and I can actually undo this. It's very easy to adjust the original Monte Carlo estimator so that in expectation, I get exactly the matrix I started out with. All I have to do is I have to rescale it up because I had a dimensional damping. And then in the end, I have to subtract an identity component, and I forgot the trace of A here. And if I do the same type of diagonal coordinate sampling after a random unitary rotation, and then if I get the outcome I can build a Monte Carlo estimator by just saying, okay, I look at this diagonal element, I have to remember that I have to rotate it because I randomly rotated it, and then I'll scale it up and then I'll subtract the identity matrix. This is now a Monte Carlo approximation technique that is unbiased in the sense that in expectation over all the randomness, I get the original matrix. And what's also nice is that this matrix is almost rank 1 and the trace is 1. This will be important later on. Okay.
So how do you said that the quantum computer does a diagonal as super A extract, but how do you implement random unitary rotation?
Very good. Can I go to the next slide? Because yes.
D here is 2 to the n.
No, D is kind of like a fixed number for now. In the next slide, it will be 2.
2.
Yes.
Oh, I thought I was understanding. Okay, maybe in the next slide.
And yeah, just for technical reasons, you don't have to sample arbitrary unitaries, but you can use some sort of quadrature, a 2 design, and get the same result. This is important for implementation reasons. But at least here, you kind of see that this type of Monte Carlo sampling works. I hope you see that.
But the dimension of the matrix A, what should I think of it? N or 2 to the N?
Here, arbitrary.
Okay. And
here is the important part now. The distribution, if you have actually an n-qubit system, oh no, sorry. If we have a quantum computer that is comprised on n of n qubits, like n is 53, then the actual underlying correlations live in the tensor product between the individual qubits, and each qubit has 2 degrees of freedom. So the matrix is a 2d to the n by d to the n matrix, but it has an additional tensor product structure that tells us the first tensor factor is the first qubit, the second tensor factor is the second qubit, the third tensor factor is the third qubit, and so on. So the axial correlations that occur in quantum computers are very, very big matrices, but they are big because they result from a tensor product of very small spaces, 2 by 2 matrix spaces. But if I take a tensor product, an n-fold tensor product, this is still going to become big, 2 to the n by 2 to the n. And there can be general correlations now between the individual systems. And so it's instructive to think of this big quantum system. The big correlation matrix is, again, something like a covariance matrix. As a 2 to the n by 2 to the n matrix, it's positive semi-definite. It has, again, trace 1. But now the 2 to the n dimensions arise from having a tensor product structure of n qubits. And you can extend the Monte Carlo sampling idea from the last slide. You can do that for each of the tensor factors independently. This is what this diagram is meant to illustrate. So I can do, just because the probabilities depend linearly on the underlying object, and if it's originally was a tensor product, then I can do this Monte Carlo approximation from the last slide for each of the tensor factors independently. And I will get an approximation, which will be a tensor product of the Monte Carlo estimators I had on the last slide. And the probabilities, the underlying probabilities, tell you about the correlations.
Sorry, can I ask you what?
Yes. Yes.
So these n unitary matrices.
Yes.
Are they? Can I think of them as just a big unitary matrix that's a tensor product of all n of them?
Yes.
And think exactly in the other world with.
Yes. Yes. Exactly. Yes. Exactly. That's okay. That's okay. Kind of like here we have like a big matrix, a 2 to the n by 2 to the n matrix. But what I'm trying to tell you is that you don't have to do a 2 to the n by 2 to the n general unitary, but a very simple one that decomposes into tensor products of 2 by 2 unitaries.
And multiplying becomes easier.
Yes, exactly. And the basis, the diagonals, also decompose into tensor products. Because the extended standard basis is just a tensor product of the individual basis elements. Okay? So what I'm trying to tell you is we can do exactly the same here, but we don't have to go to these big sizes. We can do these unitary rotations and basis measurements on the 2 by 2 matrix level. This is additional structure. And in the end, the Monte Carlo approximations will also have this nice tensor product structure. Because of linearity. And so suddenly this entire estimation process is not as scary anymore, because both the unitaries and the outcomes factorize into elementary tensor products.
Your averages of tensorized matrices.
Yes, exactly.
Tensorized with average matrices? No, right?
No, it's just like an empirical average of elementary tensor products. And now the question will be, how many of them do I need in order to get a good idea of what the original object was? But each Monte Carlo approximation itself is a tensor product.
But once you average, it stops being.
Yes, exactly. Exactly. But each of the individual ones is an elementary tensor product. And so I can actually store it on my computer. It's kind of efficient. That kind of storing elementary tensor products is not that expensive. You don't see these horrible 2 to the n by 2 to the n dimensions. Okay, that's the entire idea. And this approximation gives you on the classical side an efficient storage and contraction procedure, because each of your Monte Carlo samples is an elementary tensor product of 2x2 matrices, and each of them have unit trace. So marginalization, taking partial traces, is super easy. If I don't care about like the last qubit, I can just trace it out, and then I get an approximation of the rest.
Okay.
And no, it's good. No, I think it's good for everybody. Thanks. And the problem is, like, the left-hand side would be a horrible thing to do on actual data, because you have to do like all these unitary transformations. You have to tensor product them up. Then you have to do like big matrix multiplications and look at the diagonal. This is not something you would do on classical hardware to do Monte Carlo approximation, but it is actually native on a quantum computer. Kind of on a quantum computer, you can really view this diagram, these tensor products, as I apply a random unitary onto the first qubit, but just 2x2. I rotate the first qubit randomly. I rotate independently. I do a rotation of the second qubit. I do a rotation on the third qubit. This is what this picture is trying to tell you. So on a quantum instruction set, I really do rotate all the qubits randomly, independently at random. And then I do the measurement to get a bit string. And this is the sampling on the diagonal.
I guess the point is, when you do this operation,
yes.
each qubit,
yes.
sample just sampling diagonals,
yes.
one qubit.
Yes, each qubit you sample each qubit and you get 0 or 1. But this is kind of like the extended computational basis. This is the tensor product basis that you get this way.
Somehow these unitaries, even though they're acting on each one separately,
yes.
they somehow are capturing correlations.
Yes, exactly. It turns out that even these very structured unitaries are enough to get everything on the diagonal in expectation. Kind of like this argument still holds if the unitaries are very, very structured.
I mean, this I can see. I believe
yes.
What I can see. I don't know if I'm supposed to.
Yeah, no. The idea follows from linearity. Like for elementary tensor products, you would probably see it if there wouldn't be any correlations between the qubits. Then everything factorizes, and you can see that I can do it independently for each of the factors. But then you can write every type of big correlation as a linear combination of elementary tensor products with weights.
Okay.
And then you can just extend the argument from the last page this way.
Okay.
And this is really native on a quantum architecture. These types of single qubit rotations is something you can routinely do, and you can do all of them in parallel. And now you have a Monte Carlo approximation technique where you have like the hard part is the sampling. You've outsourced that to a quantum computer. And on the classical side, you only ever see elementary tensor products that reproduce the underlying correlations, no matter how complicated they are, at least in expectation. And now we are actually in business because we can use this to kind of learn what the interesting phenomena of our result of our quantum computation were. And maybe just very, very quickly. Bye. Now we are kind of in the realm of normal Monte Carlo approximation, concentration of random matrices. It's very easy to do some concentration analysis of how many of these Monte Carlo approximations you actually need in order to get a good idea of what's going on. And perhaps it's not surprising if you actually want to approximate the originally very big matrix, the number of samples you need to draw is proportional to the original dimension, which is very expensive. Right? If I want to approximate a big matrix with simple Monte Carlo samples, then I will need a lot of them. Right? So in this case, 2 to the n, 2 to the order n, where n is the number of qubits. So that's not very reassuring, but it's something you can't escape. But an interesting thing is, maybe you are not interested in global correlations, but maybe you're interested in what is the correlation between the first qubit and the third qubit, or maybe what is the correlation between qubit number 1 or qubit number 5, or what is the reduced outcome of my first 5 qubits, because qubit 6 to 50 might have been just working qubits and the output is stored in the first 5 qubits. So another interesting question is actually, maybe asking for a full description of all the correlations is maybe the wrong problem, because it's exponentially complex, and so we can never hope to get it, but maybe we can get marginalized information. a bit similar to what the motivation of Thomas talk was. Maybe knowing all the correlations is too much, but maybe we can get marginal information, like all 2 or 3 bit correlations. And then you can actually prove that the number of Monte Carlo samples you need in order to get, let's say, all marginals of size L, which is much smaller than the total number of qubits, still scales exponentially, but exponentially in the marginal size. So if it is 4, this would be 2 to the 4. That's not a scary number. And the actual number of qubits only enters logarithmically if you are happy with epsilon approximating all marginal correlation distributions.
Here in the sample, you also have to put random unitaries on the qubits that you
Yes, exactly. You just do the Monte Carlo averaging once. And then in order to get the marginals, you just forget all the qubits you don't care about. You kind of like just erase them from your data and then you average it. And this will give you a Monte Carlo approximation. And the cool thing is that you can use these to average all, to kind of like form all possible marginals at the same time. So you can reuse one set of Monte Carlo samples to approximate all size 4 marginals at the same time, for instance. But just looking at the qubits you actually care about. And this theorem that we published 2 years ago tells us that if you want to get all of them epsilon correct with a fixed number of n qubit Monte Carlo samples, then the number of samples you need is exponential in the marginal size you care about, inverse quadratically in the accuracy, that's the curse of Monte Carlo, but it only depends logarithmically on the actual system size, the number of qubits. And the proof sketch is actually very, very simple because
so the I is
what?
I'm a bit confused because if you put I equals n,
Yes.
then you're linear in n.
But then you have a d to the n.
It's d to the I, it's not d prime.
It's d to the L.
What's the prime?
There's no prime.
There's no prime. Sorry, that's a bad
I thought
choice.
choice.
It's a bad choice of notation. It's a lowercase l. Yes. I'm sorry. That was a very bad slide mistake. But yeah, you can see that the exponential dependence is in the marginal size. And when you let it, when you become greedy and you want to get all the correlations, then this will be. Yes. Thanks.
Is this easy to see for I equals 1?
Yes.
If I just want a margin.
Yes. Here's the proof. Maybe the proof is easier.
Okay.
Remember that like the Monte Carlo approximations were elementary tensor products. And all of them had trace 1. So if you want them 1 marginal, you just forget everything except the 1 qubit you care about, the 1 tensor factor you care about. This is what marginalization does in multilinear algebra. You just contract over everything you don't care about. But every Monte Carlo sample is a elementary tensor product of matrices that have unit trace, where contraction doesn't change anything. And you now have access to like Monte Carlo samples, which are independent random matrices in the form of elementary tensor products. And now you can always just marginalize, contract them very, very cheaply to get independent random matrices that approximate the marginals you care about. You just trace out everything. And then you do a matrix Bernstein argument on the actual marginal you care about.
But then why should it depend on the logarithm of the number?
Because I told you that you can get all of the marginals.
Okay.
And this follows from an extra union bound over all possible marginals. So, but that's the proof. Okay. And this is like, once you think about it, it's actually pretty elementary, but it tells you that if you actually think a bit about what you want to know of your quantum computation, you can, for example, efficiently extract all 4 body marginals. And maybe this is enough for the computation you have in mind. And in practice, it often is. And yeah, the take-home message is this type of Monte Carlo averaging is kind of designed to interpolate between something that is easy on the quantum side, something that is easy on the classical post-processing side, because you have these elementary tensor products, and you can use them to efficiently approximate all small marginal correlations. And this can be used in virtually every near-term quantum algorithm or quantum application where we use these early-term quantum computers as co-processors. Because at the end, you always have the readout problem. And for the applications we have in mind right now, the readout, the problem they are asking is actually approximate a complicated function that maybe tells us something about an interesting microscopic system, maybe a small molecule. And there, the actual function is always a high-dimensional quadratic form, where the quadratic form factorizes into marginals of size 2 or 4. This is, I can't go into details here, but like the problems, the quantum chemistry problems or the material science problems we try to solve with today's devices is actually always of the form that at the end you don't care about global correlations, but only about correlations of maybe size 2 or 4.
What about Shor's algorithm?
Oh, we're very far away from that. And
is it of this type, or you just care about one?
No, Shor's algorithm, actually half of Shor's algorithm is designed to tell you that you don't have a readout problem, that you can actually do a certain set of measurements, and this will tell you the answer to your original problem. But that is half of the difficulty of Shor's algorithm is hidden in there. So Shor handcrafted a solution to this readout problem. Why present a general Monte Carlo idea? Okay. And what you can actually see in these type of approximations, the Monte Carlo sampling techniques we do yield actually exponential improvements. So typically the number of measurements you need to get these types of functions scales polynomially in the number of qubits. That's not so dangerous, but you have to do it in every step of your hybrid procedure. And so this can actually be a real slowdown. And the Monte Carlo techniques we developed turn this polynomial in the number of qubits into a logarithm in the number of qubits. That was the theorem of the last page. And so you can really see that for a concrete example that was published in 2019 by the Innsbruck group, you can really see kind of like our techniques are the red and orange lines respectively, whereas kind of like existing techniques were more like the green line. And so this helps you really to speed up all types of hybrid quantum classical algorithms where you query the quantum computers many times, maybe to compute a complicated function that you want to minimize using stochastic gradient descent. Okay.
And the algorithms that existed before, they had different kinds of queries.
Yeah, they kind of did they didn't do Monte Carlo sampling on the entire set of qubits, but they just measured the first marginal they needed, then they measured the second marginal they needed, then they measured the third marginal they needed, and this is how they got this polynomial dependence on the number of qubits.
Your improvement is not just in processing the queries better, but picking
yes.
queries. Okay.
Kind of like these randomized unitaries really make a difference because the Monte Carlo approximation strategy kind of is just more efficient intrinsically. So yes, thanks. And
So I guess we're running.
yes,
Yeah.
I'm very happy. I hope that at least you understood something. Just at the very end, I want to point out that kind of like this way, these classical shadows, these Monte Carlo samplings can now really be seen as an efficient quantum to classical converter. I can take a quantum system, I can do these Monte Carlo approximations, and these I can store and process efficiently. And this allows you to do synergies of quantum computing with, for example, very, very powerful classical machine learning techniques, where the idea is to use quantum computers to generate training data for quantum problems. So in classical machine learning struggles with finding machine learning solutions to quantum problems, because almost every quantum problem is very, very difficult to solve in the first place. And so just generating training data is very expensive. If you, for example, want to solve the ground state problem in quantum many-body physics with a machine learning algorithm, you need training data, which is the solution to the quantum ground state problems for many different problems instances. But these are very difficult to come by because you have to diagonalize a very, very big matrix. And so classical machine learning is struggling not because it's a difficult problem, but because the data generation is so expensive. And we are proposing now with these quantum to classical converters, you can envision a quantum computer taking over this job. Like instead of frying your cluster in order to compute the ground state of a 100 qubit simple quantum system, you can try to use your 100 qubit quantum computer to simulate this system and cool it down on the physical level. And then you can use these classical shadows to extract training data. And in a follow-up work, we actually showed that this works provably under reasonable assumptions. And I think at this point, it's maybe best to stop. And I'm happy to take questions, and thank you for staying with me.